Alright guys, I'll go through your study guide here for you. Okay. Excuse me, I'm tired. Alright. We did most of this in class. You guys will probably just fast forward through the first few questions, but I'll do them anyway in case somebody needs to see them. So, first question, determine if the EVT can be applied. Your function has to be continuous on the intervals that they're asking about. So, rational expressions like this one do have discontinuities. They have discontinuities when the denominator equals 0. Now, I'm going to go ahead and solve this. Common mistake people make here is they forget that when you take a square root, you always get a positive and negative answer. Try not to miss that on your test tomorrow or Thursday. So there are two places where this function would have a discontinuity. One is at positive 3 and one is at a negative 3. So for our first interval here, if I'm going from negative 6 to positive 6, both at negative 3 and at positive 3, there are discontinuities. So we do not have a continuous interval here. There's discontinuities. So we would say no, the EVT does not apply to this interval because it's not continuous. On that interval. Now for the next one, from negative 2 to positive 2, the discontinuities are not there. So we do have a nice continuous interval there. So we would say yes, because the function, I shouldn't have said it, because the function is continuous on the interval. For this test, you will not only be expected to say yes or no, but you'll also be expected to give the proper reason for it. Okay? Let's go ahead and continue here. So now number 2 is where we're actually going to do the extreme value theorem, and we're going to actually find the absolute max and min. The extreme value theorem is a theorem that basically tells us that there is an absolute max and there is an absolute min for that function on the given interval. So as question 1 was just testing to know, do you know when you can even know? Question 2 is, we're going to assume, yeah, it works, so now let's go ahead and do it. So since this one we can be sure that there is a max and min, how do you do it? Well, the first thing that we're going to do is, the big picture view is you're going to do the candidates test. Now when you're doing the candidates test, the candidates means these are the numbers that possibly could be the maxes and mins. And the maximum and minimum values can occur at the endpoints, or it can occur at any critical values in between. Okay? So we need to find our critical values. How do you find critical values? You find where the derivative equals 0. So let's go ahead and find our derivative and set it equal to 0. So we do low d high minus high d low. Draw a line and square below. Now 0 times anything is 0, so that's just going to go away, and here's what I'm left with. Alright. So what we're going to do is we're going to find out where the function equals 0, or the derivative equals 0, I should say. And we're going to find where the derivative is undefined. Okay? To find out where it equals 0, basically you set the top equal to 0 and solve. So if you solve that, you get x equals 0. So there's one of our critical values. Then we also want to find where the denominator equals 0. That's where the function or the derivative is undefined. We're going to square root both sides. We're going to add 1. And then we're going to take the square root. which is going to give us plus and minus 1. Don't forget your plus and minus. Now, here's the most important thing I want you guys to take away from this. You only use the critical values that are in between the endpoints. None of these critical values are in between the endpoints, so we're actually not going to use any of them. But another little side note, which isn't as big of a deal, is when it comes to rational expressions, when the derivative is undefined, the original function is also undefined because they have the same denominator. And if the original function is undefined here, then we don't really need these anyway, because absolute mins and maxes are points that exist on the graph, and if your function doesn't exist there, then they won't work. But there are different functions where you do look for where it doesn't exist, because even though they don't exist for the derivative, they do exist on the original function. Anyway, a lot of extra blah blah there. Let's go ahead and continue on with the problem then. So on your test, you probably will have some critical values to put in here, but for this example, there are none, so we're going to skip that. And we're going to go ahead and at this point find the answers. So we're going to plug in -7, and we're going to plug in -2, and we're going to see what we get. Alright, so if I were to plug in -7, that would be 49, take away 1, so that would be 2 over 48, which is 1/24. And if you plug in 2, you're going to get 4 take away 1, which is 3, which is 2/3. 2/3 is bigger than 1/24, so this number here would be your maximum. This number here would be your minimum. Now on the test, I'm pretty sure for this question, they're going to list them as a point for this particular question. So you would see an answer that looks like this. Okay, but let's go ahead and move on to our next question. Okay, so now we're going to go ahead and find, do a couple things here with this one. We're going to find the critical values, which is where you're going to find the derivative. Set that equal to 0. And we're going to go ahead and factor to solve this. Some of us are a little bit rusty with the factoring skills. All three of these terms have something in common. You can divide an x out. That's a GCF. So when you're factoring, you always see if you could take a GCF out first. The next thing we're going to do is we're going to do what's called the box method or reverse foiling, whatever works for you. Put the first term there in the top left, last number there in the bottom right. And we'll just look for two things that multiply together to make 4x squared. It's kind of a trial and error thing. I already know the answer, so it's going to be a little bit easier for me. But there it is. Now I need it to be a -9x in the middle, right? These two numbers make that one, and then these two numbers make that one. But how do we get the middle number? The middle number comes from taking these two things and combining them. Now, this will make 9, but it makes a positive, so I want them both to be negative, so I end up with a -9. So the factored form of this thing is as follows. Okay. The next thing we're going to do is set each one of those factors, all three of them, equal to 0. So x equals 0, that's one of my critical values. 4x minus 1 will give me another critical value. If you solve that, you should end up with 1/4. And then lastly, we have x minus 2. Setting that equal to 0 gives us 2. So we end up with 3 critical values on this problem. Okay? So that's part A. Part B says find all the relative extrema. All right. So I'm going to recommend that you use the number line test for that. So we had 0, we had 1/4, and we had 2. Okay, so what we're going to do is we're going to be plugging into the derivative some test points. Notice that I'm plugging it into the derivative because I want to know what are their slopes, and the slopes help me know where the mins and maxes are at. So once again, my derivative was in factored form. I like the factored form better, so I'm going to bring this back up. But this was my derivative in factored form. And what I'm going to do is I'm just going to pick some random numbers to plug in here. Like on this first interval over here, I'm going to choose -1. So if I were to plug in a -1 for x, I would get -1 there. I would get -5 here, and over here I'd get -3. And if you multiply three negative numbers together, you're going to end up with a negative. So that means my slope is decreasing on that interval. Then we're going to repeat that. I'm going to pick a number here between 0 and 1/4. So, gosh, that's a small number. This is 0.25 right here, right? So something less than that. So I'll just plug in 0.1, positive 0.1. So we're done with that. If I plug in 0.1, I'm going to get 0.1 there. If I plug in 0.1 here, that's going to be 0.4 take away 1, which is going to be -0.6. And if I plug in 0.1 here, I'm going to get -1.9 maybe. Anyway, the numbers don't matter. What matters is that we have two negatives that make a positive. Okay, so that means that on the interval from 0 to 1/4, it's increasing. And so on. So I'll plug in 1 here, I'll plug in 3 here. Doing the math, you would find you get positive, positive, negative, so that's going to be negative, and plugging in over here, you're going to end up with a positive. So we end up with a curve that's kind of going down here, coming up here, going down there, like that. Now what that means then is that at 0, we have a relative minimum value. So f of 0 is a minimum. And up here, f of 1/4, that would be a max. And over here, at f of 2, we have another minimum. Okay? Now, on this part of your test, they're going to actually want you to find the y values. So I'm going to go ahead, what we're going to have to do now is we're going to have to plug in 0, 1/4, and 2 to the original equation. Now you could do it by hand if you want to, but I'm going to go ahead and use a graphing calculator, and you guys are allowed to use a graphing calculator as well. Let me write down what I'm plugging in over here real quick. I'm allowing you guys to use the graphing calculator because it's a good skill to have, to know how to do, and also it's just going to make life a little bit easier for us. Okay, so here we go. So to use your graphing calculator to plug these in, I mean, you probably don't need the graphing calculator for the first one, right? If you plug in 0, all these things just go away and you're left with 1, so that's easy enough. And we decided that f of 0, what that was a minimum value, wasn't it? I think. And yeah, that was a minimum. So the answer for that one would be y equals 1 as a minimum. This is the one we really want a calculator for, though. So let me show you how to do that. I'm going to go to y equals. I'm going to type in my function. All right, and then I'm going to go to the home screen by pushing second and mode. Then I'm going to go to variables, and then I'm going to scroll over to y variables, click 1, and then 1 again, and that brings up the y1. So in parentheses, I'm going to plug in 1/4. Okay, and I'm going to push enter. Now that's going to give me a decimal answer. On your test, everything's going to be as a fraction. So we're going to push math, and we're going to push 1, and it will convert your answer into a fraction for you. But it's about 1.019, right? So, but as a fraction, we would have 261 over 256. Okay? And we decided that was our maximum value. Or it's not the maximum, it's a relative max. Same thing up here. This is a relative min. And then finally, we could do 2. So you could go through the variable button again if you want to, or you could just push second, enter, and do it again to bring back the last line that we typed in before that. And then you can just put 2 there, delete the rest, push enter, and we get -3. So it can save you a little bit of time if you guys use your graphing calculator. And that was another relative min. So once again, on this part of the exam, they're just going to ask for the y values. They don't want the x values. It's not going to be a point. Should be obvious from the question. All right. Well, let's go ahead and continue here. All right. Next one says identify all the intervals of increase and decrease. Okay. Well, I'm going to bring back my number line for this. We had this before, right? So we can answer part C right away. The intervals where it's decreasing would be from -infinity up to 0, as well as from 1/4 to 2. Oops. I'll just label that as decreasing. And then the intervals where it's increasing would be here and here. So that's from 0 to 1/4, as well as from 2 to infinity. And that's the interval where the function is increasing. Okay, so that's the end of number 3. Let's continue our journey here. Number 4. Identify the open interval where the function -8x² plus 5 is concave up and concave down. So when you want to find concavity, what you need to do is you need to find your second derivative. So let's start by finding our first derivative. Followed by the second derivative. And what we're going to do is we're going to set that equal to 0 and we're going to solve, and that's going to help us find the points of inflection. Divide both sides by -12 and you get this. Reduce that. Square root. You get 2 over the square root of 3, plus and minus. Don't forget your plus and minus. So there are 2 points of inflection for this function. Okay, and we're going to go ahead and do the number line test. And you know, on a multiple choice test, if they asked you to find the points of inflection, you would probably have to rationalize this. So that would be a better way to write it. So I'll go with that. But just so you guys know, take heart. I'm pretty sure the ones on your test tomorrow, I tried to make sure they all kind of turned out to be nice numbers that are all funky and weird looking like that. But I like to keep you guys fresh on some of the basic math stuff there, because you'll probably need it eventually along the way. All right, so we have 2 radical 3 over 3, but negative, and a positive 2 radical 3 over 3. So what we want to do is we want to do test intervals here. It's a lot like the number line test, right? It really is the number line test again, but it's just a little bit different this time because we are doing concavity instead. So we're going to pick some numbers from each interval and plug them into the second derivative this time. Now this is a really weird number. I mean, if you want to punch it into the calculator, see what it is, that's fine, but this is 2/3, which is less than 1, and you're multiplying it by 1 point something. So it's not a very big number. So what I would do just to be safe is I might plug in like -3 here, 0 here, and 3 here. Now, let's bring back that second derivative. I think it was this, if I'm not mistaken. Plus 16, right? All right. And so what we're going to do is we're just going to plug the numbers in here. So if I plug in a negative 3, that's going to be 9. And 9 times negative 12 is negative 108. And when you add negative 108 to 16, you're going to get a negative number. The same thing's going to happen when you plug in a positive 3 because it's being squared, so it doesn't matter whether the 3 is positive or negative. In the middle here, if you were to plug in 0, that just goes away and you're left with a positive 16, so it's positive. So what that means then is from negative infinity up to the first point of inflection, we have a concave down function. After that, we have a concave up function. And then after that, we have a concave down again, where these points here in the middle of the concave changes are points of inflection, and that's what those are. Okay? And so identify the open intervals where the function is concave up and down. So here's how we would write our final answer. We would say from negative infinity up to negative 2 radical 3 over 3, as well as from 2 radical 3 over 3 to positive infinity. Those are concave down intervals. Whereas the concave up interval would be the one between negative 2 radical 3 over 3 to positive 2 radical 3 over 3. Okay? So that's our final result there. All right, moving on to number 5. So the next thing we're going to look at is the mean value theorem. Now the mean value theorem, it's a lot. We're going to treat this the same way I treated the extreme value theorem. With the extreme value theorem, what we did was I gave you a question first just to test to see does it apply, and then after that we applied it with another question. We're going to do the same thing here. We're going to first of all make sure that you guys do in fact know how to see if the mean value theorem can be applied, and then from there we'll go ahead and apply it afterwards. So the mean value theorem, first of all, let's review what that means. What is the mean value theorem? The mean value theorem tells you that if you have a function with some endpoints, in other words it's on an interval, there is an average slope. The mean value theorem guarantees that somewhere along that slope the instantaneous rate of change is equal to the average rate. In other words, the tangent line is parallel to the secant line. Okay? Now, we're only guaranteed that that point exists if two criteria are met. Okay? And the criteria are this. This function has to be continuous on its closed interval and differentiable on its open interval. So I care if the points in between a and b exist, and I care if a and b exist for the function itself. But I only care if the derivative exists in between a and b. I don't care if the derivative exists at a or b. That doesn't matter. Okay? Because we're not going to use those points anyway. All right. So how can you tell if a function is continuous? Well, once again, different functions, there's different ways. On number 1, we saw that it was not continuous when the bottom equals 0. When you're talking about a cube root function, which is what this is, cube root functions are continuous everywhere. So it passes the test. It is continuous on the closed interval. There are no discontinuities. Now, how do you tell if it's differentiable? Well, it's differentiable if the derivative, let me write this out. Is it differentiable? That's the question. It's only differentiable if the derivative is continuous. So in other words, I got to find the derivative of this thing. Okay? And then I'm going to see if the derivative is continuous. Now, the derivative of this thing would be taking your power, moving it to the front. Taking 1 away from your power. And then multiplying by the derivative of the inside, which would be 14x. Now I'm going to clean this up a little bit. I'm going to multiply the two numbers that are on top together, the 2 and the 14, to get 28x. The 3 is going to go on the bottom because it's a denominator. This one has a negative power, which means it also goes in the bottom. Now, having done all that, we can see that the derivative, since it has a denominator, now the derivative does have a discontinuity somewhere, and it's our job to figure out what that is. So what we do, once again, to find where the derivative is discontinuous, is we're going to set the denominator equal to 0, just like we did on the first problem. We're going to divide both sides by 3. That doesn't really matter, though, because if you divide 0 by 3, anything, you still get 0. To cancel out that 1/3, we're going to raise both sides to the third power, but that doesn't matter because 0 to any power is still 0. So really, we're just left with this. We're going to add 7, divide by 7, and we're going to take a square root. So we see that our derivative, not the function, but the derivative has a discontinuity at plus and minus 1. Okay? So there is our conclusion. So this function is continuous everywhere because it's a cube root function, but the derivative of that function has discontinuities, therefore it's not differentiable at these specific points. So let's go ahead and write a little summary of what we just discovered up here. Is this function continuous? The answer will always be yes for this function because it's just a cube root function and they're always continuous. But is it differentiable? And our answer is not at x equals positive or negative 1. Okay? So, once again, back to our question. Does the MVT apply? Well, it's going to be continuous on any interval I ask you, but if any of those intervals have positive or negative 1 in them, then it's not. Okay? So, let's go ahead and take a look. How about on part A? Part A is yes, the MVT would apply. First, once again, you're going to have to explain why. First, because it's continuous. Also, because it's differentiable. Why is it differentiable on the interval? Because these numbers, positive and negative 1, are not on that interval. So the discontinuities don't exist on this interval. Therefore, the mean value theorem can be applied because the function is continuous and differentiable for every point on that curve. Now let's take a look at number 2. On number 2, the answer is no. It's no because even though it is continuous, because as we said before, this function is continuous everywhere, it's not differentiable on the interval. Why is it not differentiable on the interval? Because from 0 to 2, positive 1's in that interval, right? And so we have a discontinuity for the derivative in that interval, and therefore it's not differentiable on the interval, and therefore the MVT cannot be applied to that interval. We can't be sure there is a point along the curve on that interval where the tangent line would be parallel to the secant line. All right, the last one's going to make you mad, but bear with me here. What do you think about the last one? Chances are, whatever you think, change your mind and say the opposite. Now, some of you guys are going to say, here's what you probably attempt to say. You probably want to say, no, it doesn't apply. But you've got to pay close attention to something. It needs to be continuous on the closed interval, but it only needs to be differentiable on the open interval. Remember that? I said that at the beginning. So check this out. Is it continuous on this interval? Well, yes. Once again, it is continuous on all intervals. So that's good. But it's also differentiable on the open interval. So here's the thing. Even though the function can't be at positive 1 and negative 1, when we're talking about the differentiability, I don't care if those are the endpoints, because for differentiability it only needs to be the open interval. So the derivative is continuous on the open interval, and so is the original function. Therefore, we would say yes to this one. Okay, so once again, for derivatives, we don't care if the endpoints are included. Now, back up for a second. Let's say we're trying to see if a function was continuous and the endpoints were no good. Well, for continuity, that matters. The function has to be continuous at the endpoints, but it doesn't have to be differentiable at the endpoints. So, just messing with your brains there a little bit. Think about it. All right, let's go ahead and progress onwards here. Number 6. So now that we've gotten you guys to practice the skill of knowing when you can and when you can't use the mean value theorem, now we're going to go ahead and actually do the mean value theorem. We didn't actually do it. We were just seeing, could we do it? Now, once again, for this one, we're not going to test to see if we can do it. I'm just going to tell you it works. If I'm asking you to do it, then it works. Now, in your actual AP exam, they may want you to see if it works first and then do it. But for this test, if I'm asking you to do it, just do it. So here we go. Well, here's what the mean value theorem says. It says that y prime, the instantaneous rate of change, is equal to the average rate of change on the interval. Our interval is from 0 to 2. Okay? So we need to find our derivative, which is the derivative of that function will be 3x squared minus 8x. And then we need to figure out what's y of 2 and y of 0. Once again, whether you want to use your calculator or just figure it out in your head, that's fine. Y of 0 is really easy. That's going to be 6. Y of 2, that's going to be 8 minus 16. Negative 8 plus 6 is negative 2. So we end up with the following then. Negative 8 divided by 2 is negative 4. We're going to add the negative 4 over. And look what we get to do again. We get to do factoring again. So, let's do our little box method thingy here. 3x squared and 4. 3x here and x here. 2 here and 2 here. 3 times 2 is 6. 2 times x is 2x. And sure enough, these can make 8 if they're both negative. So there we go. So this breaks apart into 3x minus 2 and x minus 2. If you set this one equal to 0, you're going to get 2/3. If you set this one equal to 0, you're going to get 2. Now, we only want the one that's on this interval. Now, they're both on the interval technically, but we don't want one of them, so I'll explain why. First of all, 2/3 is a shoo-in. It's in between 0 and 2. We actually don't want this one because it's an endpoint. Remember, when you're doing the mean value theorem, we don't care about differentiability at the endpoint, so I'm not going to use that as my answer. So the only answer here for this one will be 2/3. Now you got to be careful on your test. If I'm not mistaken, I am going to have the false answer in there possibly. So make sure you know not to include the answer that's an endpoint. Okay? All right. Let's go ahead and progress here. Oh boy, optimization problems. Okay, here's the problem I promised you guys would be there. We got a farmer constructing a rectangular pig pen, 500 foot of fencing. It'll be built next to an existing stone wall. We want to find what dimensions should we have in order to guarantee that we have the largest area. So here's my wall, here's the fence. I have these two sides of equal length and then this third side over here. Now, what I'm trying to maximize for my primary equation is the area of this pig pen. So my primary equation is area equals base times height of the rectangle. My secondary equation is the limiting factors that they gave me. The limiting factors that they gave me is the fact that I'm only allowed to have 500 feet of fencing. So x plus y, in other words 2x plus y, has to equal 500. So we're going to get the y by itself. And we're going to plug this in for y into the other function. Distribution gives me the following. Now I want to know what's the maximum area. Well, how do you find a maximum? You set the derivative equal to 0 and solve, and that tells you where the relative extrema are. Now technically when you do this you could get a relative minimum, but I kind of promised you guys on this test it's really going to turn out to where you're going to end up with just one answer, and that's the answer that you're going to use, so we don't really need to worry about that. A prime is equal to 500 minus 4x. Make this equal 0, add the 4x over, and divide by 4. You'll end up with x being equal to 20, I believe. We're not done. They still want to know the dimensions. That means the x and the y. So I've got x, but now I need to find y. To find your y, probably better just to go back to your secondary equation over here. We decided that x was 20. Huh? I'm feeling like that's too small. Let me think for a minute here. Is that really just 20? That's not 20. The heck? How many times is 4 going? Wasn't there one time with one left over? 2 times? It's 120, right? No. Okay, Mr. Bailey's having a brain fart. Just a second. It's 125. Mr. Bailey, you goofball. Oh, where I got 20 from. All right. Backing up a little bit. Sorry about that. So we have 4 times 125. Is that right? It's 2x, Mr. Bailey. 2x, Mr. Bailey. Okay, there we go. So y equals 250, x equals 125. Cool enough. All right, moving along. Number 8. Use the data below to determine if each statement that follows is true or false. So for these questions, I'm going to encourage you guys to draw a picture. So we have f of 1 equals 5. That's a dot at 1, 5. The derivative at 1 is 0, so that means we're going to have a horizontal tangent line. The second derivative is positive, so since this first derivative is 0, that means it's probably a relative min or a max. And since the second derivative is positive, that means it's concave up at that point. So we have a graph that looks like that kind of at that point. Okay? So now I'm going to do another one. For this one, it says f of 5 is negative 2. F prime of 5 is 0, so once again we have another horizontal tangent line, which means it's a min or a max. And then here we have f double prime of 5 is a negative 1, so that means it's concave down at that point. Okay, so it's kind of nice to draw the picture. It makes answering some of these questions a little bit easier anyway. And we just want to know if these questions are true or false. So first of all, is x equals 1 a point of inflection? Is that a point of inflection? So right here you guys got to be careful. A lot of students get critical values and points of inflection mixed up. Critical values are where y prime equals 0. Points of inflection are where y double prime equals 0. Now, for x equals 1, that's this set here where the x equals 1, right? Which one equals 0? It's the y prime, right? So x equals 1 is not a point of inflection, but it is a critical value. Okay? Now let's go ahead and take a look at part C. Y equals 5 is a relative max. So here we have a y value of 5. That's this point. Is that a relative max? And the answer is no. So that's false. Y equals negative 2 is a relative max. Right here is where y equals negative 2, and that is a relative max. So we're going to say true there. Okay? So that's kind of like what we're looking for. Now, another way you guys can tell this without looking at the graph is just by looking at the second derivative. And the first derivative. Since this is a relative min or a max at 1, and the graph is concave up, the second derivative test tells us that would have to be a minimum. Whereas over here, since the first derivative is 0, that makes 5 be a place where the min or max occurs, and then combine that with the fact that the second derivative is negative, that means that it's concave down, so that would be a relative max. So you can tell just by looking at the numbers instead of the graph as well if you want, if you think in terms of the second derivative test. All right, let's keep looking here. Let's keep looking. Use the graph below to sketch a graph of f prime and f double prime. All right. So for this function, it has a negative slope from negative infinity up to 0, and also from 2 to infinity. It's increasing on the interval from 0 to 2. So what that means is that my derivative on this interval is less than 0. Same thing over here. But in the middle place, my derivative is greater than 0. And it actually equals 0 at these points here. Okay? So if I wanted to draw a graph of f prime, how would I do it? I would make sure that my derivative graph equals 0 at 0 and at 2. So we're going to touch the x-axis at 0 and at 2. Now to the left of 0, my derivative should be less than 0. So to the left of 0, it's going to be below. To the right of 0, it's going to be greater than 0. So it's above the x-axis now until I get to 2, and at that point it starts sloping downwards again with a negative slope. So now my derivative is less than 0. So remember, if f prime is less than 0, then it's on its graph it's going to be below the x-axis. And when f prime is greater than 0, then it's going to be above the x-axis. And where f prime equals 0 at those mins and maxes, it actually is going to touch the x-axis at those points. Okay? All right. Continuing onwards. If they want us to find the second derivative as well, okay, now for this problem you're going to have to just do some guesswork. I would say this function is concave. Oh, well, let me back up. They're asking me to do the second derivative graph, right? Now, what is the second derivative compared to the function of f? Well, the second derivative is this function's concavity. So what I'm going to do is I'm going to look at the concavity of my original function. From here to here, I would say it's concave up. And then from here to here, I'd say it's concave down. And the place where it switches from concave up to concave down, I would call my point of inflection. Okay? Now, when you're graphing this on the second derivative graph, the point of inflection is where the second derivative will touch the x-axis. So that's at x equals 1. So at x equals 1, my second derivative is going to be touching the x-axis, because that's where the second derivative equals 0. Now, to the left of that point, we have concave up. So my second derivative is greater than 0, which on the second derivative graph means it's going to be above the x-axis. And for anything to the right of that point of inflection, my second derivative is concave. Well, my function's concave down, so the second derivative is less than 0. So on the graph, that means it's below the x-axis. So there's your graphs of those two functions. Okay. So for this one, I'm giving you the graph of f prime and asking you to sketch a graph of f. So we got to switch our brains up here a little bit. So here's my derivative graph. What is the derivative to what they want, f? Well, this is the slope. This graph is the slope of this graph. So at this point, the slope of f is 0. Right? And to the right of that, the slope is positive. And then to the left of that, the slope is negative. So for my graph here, I can see that my derivative, the slope, is 0 when x equals 1. Okay? To the right of that, my graph is positive, so it's going to be sloping upwards. And then to the left of that point, my graph is negative, so it's, well, the first derivative is negative, therefore it's sloping downwards at that point. Okay? Now, once again, when you're working your way backwards from f prime to f, we don't really know where this function is located. It could be where I put it, but somebody might have also done this or this. The point is that it's decreasing to the left, 0 at 1, increasing to the right. It doesn't matter how high up your function is, because when you work backwards, it's like integrating, and when you integrate, you get a plus c, which is a vertical shift. So we'll go ahead and continue here. Next question. Now this time I'm going to give you a graph of the second derivative, and you have to be able to find the original function. So once again, what is the second derivative to the f function? The second derivative is the f function's concavity. So I can see that my second derivative equals 0 at 0.5. And I see to the left of that my second derivative is positive, and to the right of that my second derivative is negative. So to the left of 0.5, we're going to have f is going to be concave down. No, sorry, up. Because over here my second derivative is positive, so that means that on this gray interval f will be concave up. And for the pink interval over here, since my second derivative is negative, f will be concave down. Okay, and this point here would be a point of inflection where the second derivative equals 0. So let's go ahead and graph that. So at x equals 0.5, so I'll call this 0.5 right here, right? At x equals 0.5, we have a change. To the left of that, it should be concave up, and to the right of that, it should be concave down. Okay, now that's one way the picture can be drawn. But the picture could also be drawn like this, just to kind of show you something else. It could be drawn like this, concave up, concave down. Make that a little smoother. Point of inflection being right here. So it doesn't really matter how they drew it, so long as to the left of that point it's concave up and to the right it's concave down. On this test, for these questions, it's going to be multiple choice, so that sort of ambiguity can be ruled out. Okay. The rest of this is your free response. I'll make a video for this portion on another day because it's getting kind of late for me, but this portion of your test will be on Friday. So I'll throw together a video for the rest of this on tomorrow or maybe the next day. Anyway, happy studying. We'll see you guys.